Hello students, myself Rupali Chaure. I am Assistant Professor of CAC Department, SRT College. Today we are going to learn about the topic registers and register transfer language, which is included in Computer Organization and Architecture subject of 4th semester. So let us start. In this video we will learn about two main topics. First one, what is register and how we use the notations to indicate different number of bits of the particular register, and the second important topic is register transfer language. Okay, and this is the next slide. Here we will learn about what is the designation of registers, means how a register is represented, how we can designate the number of bits, total number of bits, individual bits, and a portion of the bits of a register. So as you can see here in the diagram, in the first diagram, here we can indicate and register by using a capital letter R and the numeral 1. So R1 is the register name, and we use this type of rectangular shape for the indicating a register. Now if we want to indicate individual bits of a particular register, and for example our register is of 8 bit, then we will start from right hand side of the register and the number will start from 0 always. So to indicate the 8 bits we will use from 0 to 7 numbers of the particular bit of the register. So this is the individual bit indication of the register. And now here we can see that our register is of 16 bits. It is starting from 0th bit and ending on 15th bit. So total number of bits here are 16. So we always use numbering of bits from right hand side to the left hand side. So highest bit is situated at leftmost as a leftmost bit, and the rightmost bit is the lowest bit of that register. So this is also another representation for the 16-bit register. Similarly, if we want to represent a portion of the bits of the particular register, which is called subfields of any register. So if we want to represent exactly half number of bits of any register, then we can use this small bracket, and within it we can use high level bits, H for high level bits and L for lower level bits. So if our register name is PC, then with this PC we can include H in the bracket, which indicates that we want to use only higher order bits, which are the rightmost bit, just half number of bits which are located on the leftmost side of the register. So bit number 8 to 15 will be included as a higher order bits of that particular register, and bit number 0 to 7 as a low order bits of that particular register. Now for register transfer, what is a register transfer? It means that we want to copy the contents of one register to another, and this process is called the register transfer process. So we can indicate the register transfer operation like this. The source register is written here on the right hand side. The arrow sign is marked from right to left, and the destination is written here in the left hand side. So we indicate the reverse operation, means source is written on the right hand side and destination is written on the left hand side of this notation. So in this case the contents of register R1 are copied in the register R2, but the contents of register R1 does not change, means the contents exist there only in the R1. It just copies the same content, creates another copy of the contents of register R1 into the R2. And the transfer happens when a control signal is initiated and all the bits of register R1 parallelly transfers the contents to the register R2. So here we should note that the size of these registers should be same. If R1 is of 8-bit size, then R2 must be of the same size, which is 8-bit size. Okay, now note that this is non-destructive. As I told earlier, that the contents of R1 are not altered by copying them to R2. Okay, so now this type of transfer functions does not occur randomly. In the digital system, we would like to perform these type of register transfer operations on the initiation of any type of control function. Means there must be a function which is used to control or which is used to initiate such type of register transfer operation. So such type of function is called control function, and the control function is written in this manner: P colon and the transfer operation. So P here is the control function. It indicates that if P is 1, then we will transfer the contents of R1 to the R2. So P is a Boolean variable. It can have either 0 value or either 1 value. So it resumes us about the if statement in the programming language. If the P is equal to 1, then perform this operation, and if P is equal to 0, then this will not be executed. Okay, so this is the process where we perform the register transfer operation based on some control function. Now let us discuss how this control function is calculated. So hardware implementation of control transfers is shown here in this block diagram. Here we can easily see that we have a register R1 as a source register, R2 register as a destination register, and these two registers are connected by n-bit lines which are used to transfer the contents of R1 to R2. So these are called the data lines, and the size of the register R1 and R2 is n bits. That's why we write here n like this. Both of these two registers R1, R2 and this control circuit, all three are connected with the same clock pulse to perform the operation on the same frequency, and this control circuit is used to generate the value of P. This control circuit can have any type of digital system, digital module according to the requirement. So whenever the P value is calculated by this control circuit, it is applied to the load signal of this R2 register. So when P value is 1, then the load signal of R2 becomes high, and as the load signal of R2 becomes high, the contents of R1 gets transferred to the register R2. So here I have also shown the timing diagram of the transfer. This is our clock pulse, which is of T frequency. So after every rising and falling edge, it completes one clock cycle. Now for load signal, when load signal is turned on, is made from 0 to 1 during the rising edge of this clock pulse. So at time t, if we make the load signal high, then the load signal will remain high for a whole clock pulse, single one clock cycle, and then when again it will go to low to high, then the data transfer occurs. So for this whole duration, for this one clock pulse clock cycle, the transfer does not occur. As the clock pulse goes from low to high in the next clock cycle, for the next clock cycle, then the transfer occurs from the R1 to R2. Okay, so these are some points, like the same clock controls the circuits and generate the control functions, and the destination register. Registers are assumed to use positive age triggered flip-flops. Means the value of rising edge is 1 and falling edge is 0. Okay, so this is the hardware implementation of control transfers. Now in the next slide we will discuss how can we perform the simultaneous operations of register transfer. So if our registers are mutually independent, means the source register of one operation and the source register of another transfer operation are mutually exclusive, and the destination of these two are also mutually independent, means no common source and destination registers are there, then we can say that we can perform these two register transfer operations parallelly. So for simultaneous operation of this type of register transfer statements, we can use a control function. So if p value will be 1, then these two register transfers will be performed simultaneously. So we can write them with this comma in between these two transfer. So here if the control function p is equal to 1, then then it will load the contents of R5 into R3, and at the same time, same clock pulse, it will load the contents of the register IR into register MAR. Okay, so in this way we can indicate, we can write the simultaneous operations of register transfer. And here we have summarized some basic symbols for register transfer language. The first point is how to denote a register. As we have seen that for denoting a register, we always use the capital letters and numerals, like MAR for memory address register and R2 is the register number 2. So we always use the capital letter for naming a register along with the numeral value for that. The second rule for register transfer language is parenthesis. With the help of parenthesis, we can denote a part of a register. Means if we want to use lower order bits, then we can write L in between this, capital L, and if we want to write some part of bit, then we can specify a range of bits here in between this parenthesis. So for this R2 register, we only want to use the bit number 0 to 7 and for this R2 register we want to use lower order bits, means whatever is the size of R2 register, exactly half of it from the right hand side will be used here as the lower order bits. Now the next symbol is arrow symbol. It denotes the transfer of information. So source is the R1, destination is R2. So we use this type of arrow indicating from source to destination, and it is used for denoting the data transfer from source to destination. The next is the colon. We use the colon to terminate the control function. Here we have only single boolean variable p. If we have multiple boolean variables or a boolean expression, then the colon is used to terminate the control function. And the last symbol is comma. The comma separates two simultaneous operations. It can be any micro operations, like here we have specified data transfer operations, B to A here and A to B here. Okay, so these are the basic symbols which are used in the register transfer language. Thank you very much. Stay tuned, keep learning. In the next video we will learn about the bus and memory transfer. Thank you.